Yeah, hello everyone. Welcome to today's ASAP seminar. Today is the 44th one that we will feature Kwangjun Ahn, an exceptional speaker from Microsoft. He is a senior researcher at Microsoft and received his PhD from MIT ECS in 2024. He is currently working on efficient training of large AI models, focusing on optimization, architecture, and algorithmic designs. Today that he will talk about them making orthonormal updates more scalable. Let's welcome our speaker.
Yeah, thanks for the introduction. I'll be talking about orthonormal updates, what they are, what are the benefits, and how to make them more scalable. So throughout the talk, since we'll be talking about some new type of optimizers, you guys might not be familiar with the concepts, so please feel free to interrupt and ask me questions. So this is based on this new optimizer that our group developed recently called Dion. And first of all, I'd like to thank all the collaborators mentioned in this slide. So let's get right into it. When we're always we train AI models on daily basis. There's a high demand and there's a lot of compute going into training AI models, especially a lot of compute pouring into pre-training. So really important question we have to ask ourselves is, are we actually understanding how the optimization works at scale? Um, on one hand, currently we all use AtomW, and for some training code bases, AtomW is like built-in optimizer there. The popularity of Atom is shown by the number of citations it received over like last 10 years-ish. It also received the Outstanding Paper Award at this year iClear. So we love and everybody uses Atom, but a fair question to ask here is Atom really the final word, like final history in large-scale optimization or AI training in general? On one hand, people who've been using Atom, especially try to train new type of model, might have noticed this. First of all, it has a lot of hyperparameters, and depending on settings, you might have to tune all of them carefully. So it relies on some heuristics. Sometimes you have to tune the like learning rate warm up period really carefully to make it work. So there are a lot of ad hoc heuristics for people who have actually tried to make it work. But so from that, you can kind of see whether this is actually the optimal way to train AI models. Um, there gotta be, if it's like too complicated to use, you might suspect that there might be a better way to do it. And fortunately, around this time last year, there was some nice development in the community around new optimizer that kind of suggests that Atom was not the end of history. So it started out with this interesting challenge proposed in the community, I guess initiated by this person called Keller Jordan. There was this speed run challenge to train a small GPT model based on Nano GPT code base to achieve a certain validation loss. And the challenge there is to train it as fast as you can on 8 H100 GPUs. So it started out because it forked from Nano GPT code base, started out with this Andre Karpathy's around 45 minutes training time. And then community started contributing to this, starting with like Keller Jordan and other people. And there, so you can check this out on GitHub, this modded Nano GPT code base. But one of the main developments in this speedrun challenge is uh, development of orthonormal updates. more well known as Muon. It's branded as Muon. And it's like a kind of powerful new approach to training or optimization, um, training AI models. So I'm gonna tell you what this is shortly, but before I'll show you some motivating plots and results and papers that's like highlighting the power of muon. So to summarize, it seems that muon E is more flop efficient than Atom W, and it seems to be more stable. And it seems to be more friendly with large batch, which is very desirable for modern training because we're getting more access to more devices, more GPUs. And also, more importantly, it seems like it's working out of the box, as in it gives you very strong learning rate or hyperparameter transfer in general. So in next few slides, let me just show you some highlight results from the community revolving around orthonormal updates from like last 6 to 8 months-ish. So first of all, after Beyond was developed for the speedrun challenge, um, it has been investigated by many different AI labs, whether this development is whether this is legitimate or not. I guess like the first attempt was made by Kimi AI from China. They put out this report called Muon is Scalable for LLM Training, and they have this very fascinating plots results showing that Muon is about 2x flops efficient than compared to Atom W, hence leading to state-of-the-art frontier model at this 14 billion total parameter MOE scale. So it's very exciting results for us. It's telling us if you go move outside of this Atom W, you can actually achieve better compute and performance trade-off. After that, there was some effort from Essential AI from San Francisco. Um, they specifically investigated muons benefit of muon for distributed training. Specifically, they had conducted this really nice study where in this plot, y-axis is the number of devices, GPUs, and x is like the total training time in wall clock time. And as you know, if the scaling is happening ideally, or if it's like a strong scaling, if there are a number of GPUs, let's say double, then the throughput should double. So the training should shorten by total training time should be half of the previous training time. So it should really follow this 1/x trend where the number of x is the number of GPUs. And here we're showing that kind of trade-off here, y-axis being number of devices and x-axis being total training time. And you can obviously see that as the batch size becomes bigger and bigger, which is like as y-axis go up, you can see that the total training time achieves total training time for Muon achieves more favorable trade-off here. Orthonormal updates have shown to be very great for hyperparameter transfer. There are several evidence here and there. Here, let me recall the result from this Cyan paper by Pathik et al. And you can see that if you choose the weight decay parameter correctly according to science perspective, you get this direct hyperparameter transfer. There are several reasons behind like why orthonormal updates are leading to great hyperparameter transfer. For that, I'll probably recommend you guys to look at the Jeremy Bernstein's work on modular duality and modula and so on. Roughly speaking, orthonormal updates give unit update that leads to strong hyperparameter transfer. I guess the most exciting thing about orthonormal update is like it has been proven at production scale. We all know that Kimi K2 and GLM 4.5 were trained exclusively with Muon. So those are like recent highlights revolving around orthonormal updates. So hopefully now we are motivated to learn about what orthonormal updates are. So in this slide, I'll tell you briefly what orthonormal updates are. But before that, if there's any question, please feel free to ask. If not, I'll just keep going. So orthonormal updates, the idea is actually very simple, embarrassingly simple. You basically orthonormalize each step update. Here by update, it means like in your training pipeline where you call the optimizer that step. So let M be the update matrix. Here, important thing is that these orthonormal updates are only applied to matrix parameters or like more like hidden matrix parameters. For example, transformer architecture, all the attention matrices and MLP matrices and so on. But we all know that the most modern architecture comprises mostly of the matrix parameters. So it's basically where all the flops are going through. So it's important that we come up with good matrix update optimizer. So the key idea of orthonormal update is just to compute polar factor of, so here's a typo, G should be M, polar factor of this update matrix M. So what I mean by that is, so, okay, so there's a typo here, should be very confusing. So M should be G, just think of M as G. So let's say G's singular value decomposed as U sigma V transpose. Then polar factor of G is defined as UV transpose. So you first compute the polar factor of G, update matrix. And how you compute this, the most simple way is to just use a singular value decomposition, but that could be too expensive. It turns out there's a way to approximate polar factor efficiently just based on matrix multiply called new initial iteration. It looks like this, and for specifically chosen coefficients A, B, C. So repeating this initial iteration a couple times, a few iteration will lead to good approximation of this polar factor. So you can use that as a computational approximation. And after you compute the polar factor, you just update your parameter with that. So just to repeat, the main difference here is that before non-orthonormal update will basically use M, the update, like momentum, or like it could be the momentum that scale with the variance, just like atom. But in the case of orthonormal updates, you'll take that update matrix and further process it by computing the polar factor of it and use that to update the parameter. So this surprisingly simple idea turns out to be very effective. And I would like to ask audience just to like make the presentation interactive, why this very simple idea is effective. So if people in the audience have any idea, please feel free to contribute and yeah, unmute yourself and contribute. So I guess my question here is like, why is this simple post-processing of the update by computing the polar factor so effective? Anyone has any clues? Um, if no one's willing to volunteer, I can just keep on going. I thought it would be fun to kind of be interactive here. So just to like kind of uh, someone wants to like share. Um, Yeah, I'll just keep on going. So the answer right now, as of now, nobody really knows why this orthonormal updates work so well. So I think it will be really great research question moving forward to figure out why orthonormal updates are. Yeah, there's some pieces of evidence here and there. I like the aspect perspective taken by Jeremy Bernstein and a collaborator. But it would be really nice to get to the bottom of why orthonormal updates are so effective. So we have seen all these great results about muon and orthonormal updates family, showing this great benefits of flap efficiency, distributed training friendly, and hyperparameter transfer, and so on. So is like muon really the candidate that dethrones Atom here? Um, Unfortunately, Buon, this current orthonormal update, um, is quite susceptible to become compute bound at very large scale, especially for dense layers. So, for example, if you look at Essential AI's benchmark result, you can take a look at that from this URL. They did extensive benchmark result and show that at Llama 405 billion scale, um, the B1 is quite difficult to make it work because of precisely because of this requirement of Newton-Schultz um, needing for this dense matrix multiply iteration. And as matrix size become larger and larger, for example, the MLP matrices with MLP expansion vector, at like 405 billion scale where matrix size easily become 20K and so on, this iteration becomes compute bound. Here's like a one benchmark I did locally on my GPU. So you can the x-axis is the matrix size. I'm just doubling each time and just measuring time per step. And just because this Newton-Schultz iteration, it's a super polynomial iteration. So it's reflected in the benchmark as you increase the matrix size about around like 3K, it becomes very, very expensive. Imagine doing this for all the MLP matrices in your architecture. On the other hand, we all know that Atom, being a coordinate-wise optimizer, it doesn't have such bottlenecks. So then, although it has been successfully applied to MOE architecture so far, as the MOE matrices get bigger, this micro benchmarking or essential AI's micro benchmarking as well is showing that we will soon hit the limit with the orthonormal updates. So we might maybe have to abandon orthonormal updates for large MLP matrices and so on. So we'll like hit these challenges. And I think this can be happen in foreseeable future. So given that, um, orthonormal updates or muon cannot be like direct replacement of Atom for now, and begging the question of can we make orthonormal updates more scalable?
I have one question.
Yes, please.
Yeah, so for MOE model, I think there's a trend towards fine-grained MOE where each express size is becoming smaller, and this is good for muon, right?
Yes, statistical performance wise. You mean like as a MOE models like matrix becomes smaller, its performance gets better trend?
Yeah, because there's a clear trend toward fine-grained MOE, and each express size is like bounded, and this may be a good news for Myung.
Yeah, I guess like if matrix size becomes like smaller and smaller in the future, then I guess yeah, just current Schultz would not be a bottleneck per se. I don't see too much problem with that. But as the model gets bigger and bigger, I do see like some components of the model become like dense, and they're like might have to just apply atom, then break the benefits of like these orthonormal updates. So I guess we're kind of bulletproofing orthonormal updates because just because it has a lot of great benefits, can we actually surface it as a direct replacement, dethroning atom, right? So that would be like kind of yeah. I guess to be fair, like academic setting, models are small enough that I think mu1 should be sufficient as well. Any more questions?
I think there's a problem like the current large model often have very sparse experts. So basically they have very short, very small like active parameters, like maybe 20B, and they will have like 600B total parameters. So the big part is actually the MOE part. And as Sony has said, we have fine-grained MOE, so you have very small matrix for the expert. So I'm not sure if the matrix size is actually a bottleneck for the computation. If we are doing a very sparse MOEs, and yeah, and also fine-grained MOE.
Yeah. Oh, yeah, I agree with that. As I said, if your architecture matrices are all small, I guess like not exceeding this infeasibility region, I think it's okay to not do anything and just apply full dense Newton Schultz.
Yeah. Even for the fine-grained MOE setting, I guess the tension layer could still be a bottleneck. We still have the dense Corey p-value projection matrix, which could scale along with the model dimension.
Yeah, I mean, we'll have to see what future holds for us, but we are just exploring like subset of like approaches, and it's not clear whether like the ground truth architecture should have all small matrices. If that's the case, I guess there's no system bottleneck for uh, entire Newton Schultz, but I really don't know, I guess. Any more questions? Those are very helpful feedback. If not, yeah, I'll move on. So that's like the type research question we're trying to answer here. So can we come up with more scalable orthonormal updates that can work with this like very dense and large matrices? So the approach we're taking here is we're introducing new scalability levers in the called the low rank factor. So we're only orthonormalizing the low rank fraction of the entire subspace. To do that, we're rethinking linear algebra in this orthonormal updates. First, we compute the low rank sketch of the momentum or the update, and then we orthonormalize that instead of the entire matrix. So you're only orthonormalizing fraction of subspace. But then you can think that, oh, we're only orthonormalizing the fraction update, so it might lead to poorer update quality. But actually, the key in our approach is to use error figment mechanism to capture the part that's not captured in this sketch, and you feed it back to the momentum buffer such that across the multiple iteration, it will be captured and be reflected in the update. So the error feedback mechanism is actually really important, and I'll tell you what exactly it looks like. It's really important for the compensating for the reduced optic quality due to low rank. So in our optimizer Dion, we use the amortized power iteration to sketch this low rank. And notably, there was a recent work, I came across this recent work which developed Trion or Trion, whatever it is. They use the discrete cosine transform to sketch. It's a more, I guess, computationally lighter approach. So those who are interested, you could check it out from this link. So for the remainder of the talk, I'll tell you what Dion does and what can Dion do. So all the results and benefits. So let me first show you the benefits of going low rank. So obviously, as I prefaced, it leads to better scalability by having this additional axis of low rank factor. It enhances scalability. And also, we'll touch upon this towards the later part of the talk, but it leads to less communication overhead, which could be specifically of interest for hybrid sharding strategy case, where within the node you're using the FSTP, and across like data center you're just duplicating the DDP. But for now, let's focus on the scalability in terms of compute. And here's the so I show you the mu1's scaling behavior when matrix size double. And now I'm adding the Dion with the rank fraction, low rank fraction, half, fourth, and eighth. And you can see that it just leads to, just because we're orthonormalizing the fraction of subspace, it strictly leads to much less wall clock time overhead. Dion has this benefit of like having nice distributed implementation, just because the low rank orthonormalization is not of a bad bottleneck. Now all we have to care about is the amortized power iteration, which happens to be very shallow matrix multiply, such that we can come up with very efficient FSTP compatible or FSTP times TP compatible implementations. There's some algorithmic flexibility with Dion, just because we're also capturing the low rank with the amortized power iteration. There's some flexibility we can leverage to come up with even more efficient implementations. I won't have time to go over these versions. If you're interested, please check out our paper. So let me go deeper into this low rank factor thing. So we introduces the rank density factor or low rank factor between 0 and 1. Let's call it alpha. And let D be the dimensionality of the matrix parameter. Then Dion alpha update is constrained to be low rank, where the rank of update is alpha times D. So for alpha half, it'll be D over 2, and alpha equal to a fourth, it will be D over 4, and so on. This leads to faster computation, which we just saw from the plot. And actually, there's a benefit from communication as well. Nice thing about the Dion is that we can actually go sparser at larger scale. This is some scaling study we conducted. So every time we roughly triple the number of parameters, we see that there's a less gap between the aggressively sketched Dion. So like you can concretely see 1/6 Dion versus half Dion gap. And also there's a mu1, I guess, as a benchmark. And you see that the gap becomes narrower and narrower across scale. And you can actually concretely see this by tracking, like, for example, half Dion, and the gap between mu1 and half Dion also narrows across scale. Some people might be wondering how it performs for post-training. We actually have tried a list for SFT post-training. And the moral story here is that it seems like the benefit of orthonormal updates holds out for SFT. we haven't seriously tried reinforcement learning post-training, but given that some of the production level language model that's trained on mu1 also did RL post-training with mu1, I think mu1 is also a viable option for RL post-training. So here I'm showing some plots that demonstrates that Dion retains benefits of mu1. Practically both mu1 and Dion and all this orthonormal updates optimizer, you only need to tune the learning rate as opposed to Atom where you have to carefully tune like some beta parameters and so on. And just like we saw with the Cyan paper's results, Dion also inherits this benefit of strong hyperparameter transfer. So I think this is a benefit shared across different orthonormal update optimizers, which is really nice. In this slide, I'll quickly talk about like what the Dion update rule looks like because I only verbally described it earlier. So mu1, as I kind of informally introduced earlier, basically keeps around this momentum buffer, and then you use Newton-Schultz iteration to compute the polar factor or orthonormalize the update to compute O, and then use that to update the parameter. So as I shared earlier, the Dion or low rank orthonormal updates are using the goal is to come up with the low rank orthonormal updates. So what we do is basically we keep around the buffer same way, but then here we sketch rank R factor of MT using a single power iteration to compute the LTRT. So LTRT are both rank R matrices. And then, as I alluded earlier, we compute the approximation error. The important aspect of Dion or this low rank orthonormal updates is that you keep around this error feedback. And you will find the exact same error feedback in like this recent work that I mentioned earlier, Trion paper. So this is actually very important. I'll show you some ablation study later. Without this error feedback, your low rank orthonormal updates will degrade noticeably. And then we use LTRT so in this case of Dion, you can simply just column normalize and then you will get the orthonormal updates. So let me show you like the ablation results around the key algorithm components of Dion. So two questions here is that those who are familiar with the power iteration or subspace iteration, for it to be more religious, you have to run it for longer number of iterations. But we actually do the sketching, low rank sketching with just single iteration. So you might be curious whether single iteration is enough. And the second question is, I kept emphasizing the importance of error feedback mechanism, and can you actually show me that? So here are the two ablations. For example, first of all, I compare the Dion versus SVD. SVD low rank sketching will be the exact low rank sketching. And in our ablation study, SVD version of Dion leads to almost same convergence as our single power iteration of Dion. So it demonstrates that single power iteration was pretty good enough. And more interestingly, here's the ablation for with and without error feedback. So Dion, which does error feedback, achieves a lot better update quality than error feedback version of Dion, showing that for low rank orthonormal updates to work, you really need error feedback. Any questions so far? Okay, so I'll address the point that I mentioned earlier regarding the reduced communication. So since like the update is constrained to be low rank at a high level, during the DDP data parallel, you don't really have to share async the entire n by n gradient matrix, but only the low rank factors. That's the high level idea of what we're doing. So we're only synchronizing low rank matrices, and you can achieve mathematically equivalent update as if you were synchronizing the entire matrix. And we see this being useful for hybrid sharding strategy, where you do FSTP within nodes and then across nodes you do replicated data parallel. And I think this strategy is useful for a certain scale for flop utilization. So the way we do here is that instead of like syncing the n by n entire matrix by only syncing the low rank factors, you can save this to n plus n times r. Yet it leads to mathematically equivalent update, so you're not losing anything. So we hope that this proves useful in large scale when people actually train models with hybrid sharding. So we fully open source our implementation of Dion. You can find it in Microsoft Dion codebase. So what we implement in the codebase is both Muon and Dion, because our goal is to make the orthonormal updates more scalable. Because as I said earlier, for practically small matrices, Muon should be sufficient. So you could enjoy our codebase by using Muon for that case. But if you happen to have really dense matrices, large matrices, you can give Dion a try. And nice thing about Dion is it has like very natural way to do two-way sharding, handle two-way sharding, like FSTP plus TP. So we have that implementation in the code base too. And for Muon, we implemented all-to-all version due to Essential AI for PyTorch FSTP2. So we also implemented this compressed DP sync, the feature of Dion that I mentioned earlier regarding we are only syncing low rank factors, hence saving the communication. We put in a lot of efforts to come up with a clean code base. So hopefully this is useful, and for all the details you can find in the README section of the code base. Our code base was endorsed by Andre Karpati. So that's everything I have for today. Hopefully you learned something about orthonormal updates, what the benefits are, and what the challenges are, and what low rank orthonormal updates brings to the table. Thank you for your attention, and if you have any questions, please feel free to ask right now.
I have one question. I don't know if I missed something, but could you elaborate on the detail of the like single iteration of the low rank factorization?
It's based on the power iteration. So you hit the momentum matrix from the right side by the low rank factor. Yeah, and you get out, and you can orthonormalize this low rank, the output of this matrix multiply with Newton Schultz or QR factorization. But now you're applying Newton Schultz on the smaller, like let's say n by r matrix. So that's where the computation saving comes from. and then you use that resulting matrix and hit the momentum matrix from this time from the left side. And that's how you get LR vectors. Does that make sense?
How does the low rank submatrix obtained from?
Initially you like start with like randomly initialized. But then in Dion, we actually keep around this right vector across iterates as an optimizer state. So you actually, that's why we call it amortized power iteration, where warm starting power iteration from the result of RT that comes from the previous iterate. So that's the reason why Dion can achieve like SVD quality low rank sketch with just single iteration of power iteration.
Okay, thank you for your answer.
Yeah, thank you for the question.
Yeah, maybe I can also ask one question. It's about recently I heard some people say that methods like mirroring seems to just means that I like it seems to lead to although more faster coverage, but maybe at the end of the training it seems that it still and performs Adam. Do you have any comment on this issue?
Yeah, I think I also came across several papers on this. And I guess, well, I mean, like it all depends on the setting they're running on, right?
Yeah.
That's one thing. And another like circumstantial point that I have based on like I see all the results out there is that I think it has to do with the batch size and all this advanced optimizer really shine with large batch size. This essential AI paper actually did really careful hyperparameter tuning. So you can check out the paper and see the credibility there. But to my eyes, they were doing really great job. So if you believe their results, it seems that they kind of collapse for low GPU regimes, which means like they probably chose a smaller batch size to maximize the GPU realization. And as you increase the number of batch devices, so obviously the batch size, optimal batch size will increase. There's a more noticeable gap. And I think this is where you should be using advanced optimizer too. Which kind of makes sense because like with the large batch size, the optimizer, that step time is becoming less and less challenge because forward backward passes becomes more major and major. But anyways, in any case, I think we might be seeing is like something along the like I really don't know, but my guess is that you might be seeing this regime if you can trace my cursor, yeah, where like Vion and Atom like kind of collapses for a small number of devices or low batch regime.
I see, yeah. Just I think that seems people still need to understand the scaling law with the new optimizer. Yeah.
Mm-hmm.
And another question is about some recent papers says that, for example, mirroring lead to better memorization about maybe some long tail knowledge. Yeah. So my question is about beyond the perplexity, is there some more maybe advanced way to further identify the difference between the mirroring and maybe the Adam? Yeah, just means that they should have some different behavior, not only the perplexity only. Yeah.
Yeah, that's actually a great question. I think if even if like if you look at this paper, Uniscalable, for large training, their appendix has like probing results of like the matrix spectrums, and like they obviously give you like different matrices, like the trained models spectrum of the matrices are very different. So it definitely learns different model, and people are starting to look at like what kind of solution this different optimizer found. Um, I think it's really interesting question. We're only scratching the surface of it. I mean, me personally thought a lot about how to make things more scalable. So I think I'm not the right person to ask for that question. Um, but there's something to be discovered for sure. But yeah, sorry for not giving you any further
No problem.
additional information
Yeah,
on
I
top
think
of
the
it. Yeah,
new
but you know,
question.
But I think it's a great question. I just don't know because I haven't thought about it, and hopefully people think about it more and get some more results.
Yeah. No
But
problem.
then
I think that's a new
I
question.
guess like before just because I spent some time thinking about this, I must have been convinced like why this is nice. Among like all this like circumstantial evidence, to me, like after I read through like Jeremy Bernstein's perspective on like this like modular duality and stuff like that, I think it's a very canonical approach to treat the matrix parameters because matrix parameters vector transformer input activation gets transformed into output activation. And also, I do think that with this canonicality of like canonical property of this orthonormal updates, I think it has a lot of benefits beyond what we're seeing. It leads to stable training, activation remains stable. It has been demonstrated in multiple works. So maybe it will lead to like very stable training in the future. So maybe benefits not just from the fast training, but more from stability and so on, robustness.
I see. Yeah.
Mm.
Yeah, I think this makes sense. Yeah. Thank you for answering.
Yeah, I think a great thing about this direction is like Jeremy and like other collaborators who are excited about this really like wrote a lot of nice blog posts about this. So you can easily find like convincing evidence here and there to like kind of further convince yourself why orthonormal updates are like really strong competitor for Atom.
I see. Yeah. And I think maybe another question I guess that maybe would be interesting is about if the model trained with mirror and the DAM that have different behaviors, maybe we can also find some maybe post-training ways to maybe convert the checkpoints between these two ways. Yeah. Because I think
Yeah.
that if you just, for example, if you pre-train with Adam and then you switch to mirror in post-training, that the model is not very good. Yeah.
Yeah, that's another thing people should like look into, like whether there's so in our like SFT, I mean it's a very small scale. Like, do you remember like the post-training to be scale result? I can get back to that here. Yeah. Here, like we're post-training gamma 2B, which for sure was trained with Atom. And we didn't see much like incompatibility for SFT at least. But also like this small scale and like we haven't tried like anything larger than this. So I cannot really vouch for orthonormal updates for post-training Atom pre-trained model. But we'll have to see. I think again the Buon is scalable for LLM training paper by Kimi also pointed out that there's some incompatibility issue, but
Yeah.
he didn't share like further evidence there either. So I think it's kind of up in the air at this point.
Yeah. I think this makes sense. Yeah. Thank you very much.
Mhm.
Yeah. I also have several another question.
Sure.
You said Mill was founded by the uh, when the matrix size becomes larger, Mill suffers from like the compute bound issue.
Mm.
I was wondering, like, do you think like NIC iteration is stable enough for FP4 computation?
For like with the orthonormal updates.
Yeah, this iteration because now we have FP4 my matrix multiplication, which could be much
Mm.
faster than before.
So actually for that, I think the right perspective, let me actually like change your perspective a little bit. Instead of making the muon update um uh like low precision to speed it up. I guess that's a point of your question, right?
Yeah, like
Yeah.
whether low
Yeah.
procedure muon upgrade.
Maybe like muon updates are robust against low precision that
Yeah, kind of.
um okay, the answer to that question I don't know. But I think uh okay, yeah. So the answer to that question, I actually don't know. Currently, it's done with BF16 usually, even in the speedrun code base. FP4 is like too aggressive, and just the nature of like orthonormalizing, it's like um, linear algebraic operation. So usually doing FP4 for that might not be good. But then you might say, oh, like maybe like it's not practical approach for the future. But okay, so like going back to my like point that I wanted to say before this was I think the right way to think about this is like orthonormal updates or quality optimizer, right? And it really leads to stable activation. So I think the right way of thinking about this is like we keep the optimizer.step in a higher precision, which lets us do forward backward passes very stably in low precision. So that's actually I wouldn't be surprised if like spending a little bit of more time during the forward backward passes than Atom by using orthonormal updates leads to very stable training, which lets you go low precision for major compute like forward backward passes.
Yeah, thank you for your answer.
Yeah, thank you.
Any further questions from the audience?
Do you have some like quantitative analysis of like when does the DM faster than mu, like for the
Well, I mean, okay, I mean, I guess it's all the answer is like always faster, but then like for small matrices, like this like compute was not bottleneck. So like it's not gonna give you like much difference. Um, but it's more about like you have to like measure this against like the entire training pipeline. Because like right now I'm just doing the optimizer step micro benchmarking. So it really depends on like your configuration. But what I said about like Dion not useful is like I guess for small matrices, Dion's wall clock time was not overhead at all already. Um, yeah, but I think a critical threshold around like with the H100s is like I think 10K or like 20K around that regime. I think beyond that, I think generally this like matrix multiply iteration becomes too much. It becomes compute bound.
so you mean for 10K input
Like you
dimension?
mentioned getting bigger than like 10K. I think that's my belief based on the like micro benchmarking.
Oh,
But I mean, also it depends on like right software engineering, right? So if you really over like computation and communication really carefully and make them really compact, maybe you can get away at the scale as well. It's not like, oh, this question is very like subjective in some sense.
so you mean for 10K, the low rank is actually not helpful for
No, I'm
the,
saying like beyond 10K, low rank should become more and more helpful.
but 10K is very large, like if we, yeah, I think, yeah, 10K is kind of large for a matrix input dimension. Is that what you say for input dimension?
Not in input dimension, like for example, like I don't know, like concretely Llama 3405B model. Uh, it's like it's a hidden dimension is like 8K, I guess. And then the MLP matrix is could be like 32K
Yeah, yeah.
across the expansion dimension.
Okay, that's a depth model. Yeah, cool. Yeah,
Yeah, yeah.
yeah, definitely cool. Yeah, thanks. Mhm.
Is there any more questions? If there's maybe no more questions, I think that maybe we can end today. Yeah.
Yeah.
Thank you very much for your time. Yeah.
Yep. Thanks a lot.
Yeah, thank you for your presentation.